Hey everyone, we're going to be looking at section 3.9 and 3.10. 3.9 is on logarithmic and exponential functions, and also we look a little bit at logarithmic differentiation, which is a pretty cool little tool that we can use. And then we're going to move on to 3.10, which is inverse trigonometric functions. And then at the end, it talks a little bit about derivatives of inverse functions themselves, just in general. Okay. So let's jump into these logarithmic and exponential functions. Now we've seen a little bit of this already. We've seen the derivative of e, and that was the easy one, derivative of e to the x and c to the x. But there's the also the other side of that, which is the natural log, which is the inverse function of the exponential function e. And then we have our other bases, our non-e bases that we also need to look at. So we have our rules, which are on your rule sheet. So the derivative of e to the x up in the right corner we see is e to the x, and to counteract that, the other side of that is the natural log. So the derivative of the natural log function, so ln x over on the left, is 1 over x. So pretty easy to memorize and a really useful tool. We're going to see this pop up a bunch later on, and it actually works its way to other forms, as you see down here with the other non-e bases. Ln x and 1 over x are key component to a lot of things in calculus, especially when we get into chapter 5 when we start doing some integration. It's going to pop up a bunch because of that 1 over x idea is really kind of a key thing. So the derivative of ln x is 1 over x. Okay, so for the non-e basis, so we'd let b be a base b which is greater than 0, not equal to 1, and not equal to e. So we ignore the e, even though if you plug e in, notice if I plug e in, ln e is 1, so it goes away, and ln e is 1, so it also goes away here. We just say, well, it's not e. So it's got to be greater than 0 and not equal to 1 nor e. So for here. So log base b of x, so like log base 2 of x or 3 of x, pretty much it works out very similar to the ln, but they flip places, and we take the 1 over x times the natural log of the base itself, so whatever number was in there. So the way I always remember it is they pretty much flip-flop. The base goes into the natural log and x comes out, while all under 1. Then if we take the derivative of any exponential function with base b, derivative of any exponential function with base b to the x is b to the x times that natural log of that b itself. Okay, so it follows along. Okay, so we're going to look at I think 2 examples I have on here for this. And so we can see these, and then we're going to move forward. This video, so I'm going to try to keep this video short. Again, these are just rules that we're going to practice. I mean, there's not a lot of in-depth discussion has to happen with these. It's going to take practice to get these down. So the first one, we're looking at the derivative with respect to x of ln x squared to the x power. So I notice I have a quotient here, so I'm going to do the quotient rule, so the higher being the natural log x squared and the lower part being x. So if we apply the quotient rule to that, so the lower times the derivative of the top, so the derivative of ln x, so anything inside ln, when I take the derivative of ln, becomes 1 over whatever was inside. So ln, whatever is inside, becomes 1 over that whatever was inside. And then I apply the chain rule on the x squared, and I multiply by the derivative of x squared, which is 2x. That's why I get the 1 over x squared 2x. The 1 over x squared is the derivative of ln of x squared, plus with the chain rule, I multiply by the 2x. So that's the lower times the derivative of the top, minus the top times the derivative of the bottom, which is 1 all over the bottom squared. Okay, so a lot of things cancel. These 2 x's cancel with that x squared. That 1 goes away, and we're left with just 2 from there, ln x squared over x squared. And remember, these x squareds don't cancel because that x squared is inside of the ln. Okay, we maybe could do more with this. I'm fine with just leaving it as that, but just kind of, you could take out a 2 or that kind of thing. There's no need to. We got it reduced down pretty well. We'll move on from there. So let's look at a different example with the log base b and an exponential with base b. So we hear a lot of times people get kind of confused, but remember, logarithmic and exponential functions, they work well with each other and with their own selves as long as they have the same base. So if we notice in here, I have an exponential here and a logarithmic function here. And notice this one has base 2, this one has base 3. Since these have different bases, they do not get along. So we can't try to combine these or put them together or pull them apart, and we have to treat them like they're totally different functions. Okay, so since I have two different functions, they're being multiplied, I'm going to do product rule. Now notice this sine x is hanging out here too, but notice it's inside that log function, so I'm going to let it run with the log function and do chain rule with that. So if I do the product rule here, first times derivative of second plus second times derivative of the first, we'll get first times the derivative of the second one. So log base b of anything is 1 over what's inside times ln the base. So the sine x goes down, so 1 over sine x times the ln of the base 3. And then chain rule on the sine x times derivative of the sine is cosine, so I get cosine x up there. So this parentheses here is derivative of that log base 3 function. Okay. Then the second one times derivative of the first. So 2 to 3x minus 1, the derivative of log base or exponential base b is itself times the base or ln of that base b. And I missed a 3 there too, didn't I? So I missed a 3 there. So let's see. I'll have to add in that 3. I'll put a 3 up here later, here in a second. Okay. After that, we can reduce this down. And I'm sorry, that 3, if you didn't know, comes from that chain rule in the 3x minus 1. So I missed the 3 there from the chain rule there. Okay. From there, I break it apart. I can pull out the 2 to 3x minus 1 is there and there. So I'm just going to pull out front to clean up a little bit. This cosine over sine reduces the cotangent over ln3. ln3 sine x times 3 ln2 all goes right there. And we have pretty much our reduced form. I don't think it goes any farther. I mean, you probably can go a little bit farther, but that's just already kind of messy already. Okay. All right, moving forward. Okay. Logarithmic differentiation, last part of 3.9, is kind of a side tool that we can utilize sometimes where we're looking at and utilizing the property of logs. There's some specific properties of logs. If you remember back, there's the product rule, the quotient rule, and the power rule. Okay. And product and quotient rule are great for combining. Expanding, there's not a lot that can come from it. Sometimes expanding does help. There's going to be an example I'm going to point out here in a second that shows expanding does help. But by far the biggest help that logarithmic rules can help us with the differentiation is the power rule itself. So one great example, kind of a basic example when you first look at it, but when we think about it, it's kind of difficult to work with, and that's the equation y equals x to the x, or the function x to the x power. And if you think about what is x to the x power, well, it looks like a polynomial because there's an x to some power, but since the x also is in the power itself and it's changing, it's not a polynomial, meaning it doesn't stay the same throughout the whole function. So it's not a polynomial. And it might be an exponential because there's an x in the exponent, but if you think about it, the base is x, which is changing, so it's not an exponential. So it's not an exponential, it's not a polynomial, it behaves different. Okay, so this is kind of going into a different class of functions that we can't do our normal rules with. So we kind of think back, well, how can I rework this or change it to something that looks a little bit more familiar? Well, the power rule allows us, on logs, allows us to bring anything out of the exponent or out of any power out front as a constant multiplier or a multiplier in general. So something we can do is we can use logarithmic differentiation by taking the log of both sides. Normally we stick with natural log unless there's a specific base that we see we can cancel, which is very unique cases. So we take the ln of both sides, which is completely fine. I mean, it's a function, it's defined, so we can do this. And in doing that, that allows us to take this x out front using the power rule of logs. And so now we have the x out front. And now we have three functions, ln y, x, and ln x, which are all easily differentiated. We know how to do these. We do the rules. So the derivative of ln is 1 over whatever was inside. And then since this is non-x itself, we're going to take the chain rule and take the derivative of y, which is the y prime. So taking the derivative, ln y, 1 over y times chain rule, derivative of y. And then over here I have product rule, 1 times x times ln x. So first times derivative of the second one, ln x is 1 over x, plus the second one times derivative of the first, which is 1. So I get the product rule here. Notice x and x cancel, the 1 goes away, so I end up with 1 plus ln x there. I bring the y over by cross multiplying it over, and I get y prime, where the derivative of y is y times 1 plus ln x. And we know what y is. We originally had it up here, so we plug it in. We end up with the derivative function x to the x times 1 plus ln x. So logarithmic differentiation is a way of using logs, properties of logs, to break apart, rewrite certain functions and equations such that it allows it to be a lot easier to differentiate. And a great example of that, beyond just the power rule like I did here, is sometimes using quotient rule, which is on, let me make sure this page is right before I go any further. I think it is. I think I put the right page on here. Hold on, right beside me. Page 210. Page 210 shows you, example 8, a great example of how logarithmic differentiation can be used to break apart functions through logs using the product and quotient rule. And they even implement the power rule also in there, so it uses all three rules. Great little example. After you see it, it's pretty straightforward. Now, most of the time, that process of logarithmic differentiation, it's not a necessary use, meaning you don't always have to use it in the way it's doing in this example. But it shows you in this example, sometimes it makes it a little bit easier to actually differentiate, and it ends up in what we call our factor decomposed form. So if you notice at the end of example 8, it has the derivative of f with part of it already factored, so factor part already pulled out, and then what we factored from is in partial fraction decomposition, if you remember that from 171. So that's kind of a cool little thing that does result from logarithmic differentiation that will pop up later on down the road. We won't see it a lot here, but it's a really cool tool. And you also can see how it makes it a lot easier to differentiate that. The example 8, if you try to do, if you notice, you'd have to do product rule on top and quotient rule and the whole thing. So it would get really messy. So the logarithmic differentiation allowed us to bypass that mess and already give it in factor form, which is really nice and neat. Okay. All right, moving on, we're going to look at 310. 310 starts with our inverse trig functions. So if you remember, inverse trig functions are where you have that -1 there, which is not like the reciprocal idea. This isn't sine of x to the -1 power. This is the inverse function from sine. So it's not a multiplicative inverse. Be careful, keep that in mind, okay? And so with these, remember, if I take sine x, I'm plugging in an angle, I get a value on the unit circle that results from that, or on a graph, that kind of idea. So inverse trig functions are, we're plugging in some value between -1 and 1 that will give us an angle. And remember, sine and tangent, so therefore cosecant and cotangent result between -pi/2 and pi/2, not including for tangent and cotangent. And then for cosine and secant, it's between 0 and pi, including. So that, remember, that's that top half of the unit circle and the right half of the unit circle if you think back to 172. And so when doing these, they have some good proofs in here. I'm not going to go through the proofs as I haven't in the past of these functions, and they're pretty easy to see. If you think about it, you can kind of look at these and see some roots going on in here. And if you think, well, where are these roots? Well, these roots are coming from Pythagorean theorem. I mean, it's a relationship between sine, cosine, and all those good things, and it's pretty straightforward to see. So the hard part of these is not doing them, it's memorizing them. That's kind of the hard part. And you can see these formulas aren't the prettiest thing. The great thing, though, is you can remember 3, and then you can remember the other ones. Okay, this is very similar to how I've showed you in the past. So if you notice, sine, secant, and tangent are the positive forms of cosecant, cosine, and cotangent. So with the C ones, we plug a negative onto the S, or sine, secant, and tangent. Okay, so sine is 1 over root 1 minus x squared. Negative, same thing for cosine. Secant is 1 over absolute value of x, square root of x squared minus 1, and then cosecant is the negative of that, and then tangent is 1 over 1 plus x squared, and cotangent is negative of that. By far the biggest one we'll see later down the road is this tangent one, if not the cotangent. Cotangent not as much because we can always manipulate a cotangent function to become a tangent just because there's a negative attached to it. This tangent one pops up a bunch because that 1 over 1 plus x squared, that's a very familiar looking polynomial or rational function. Okay, with the roots, not as much. Okay, so performing these, basically, it's basically a formula. You're following the formula, you plug it in, and if there's more to it, meaning there's like an extra function inside, or this is a function inside of another one, just got to pay attention to the chain rule. So an example, I think it's the first problem on the worksheet. I just went ahead and did that one so you can have it and kind of see it. Inverse cosine of negative 5x to the third. So if I take the derivative of this, I'm taking the derivative of an inverse cosine function with negative 5x cubed inside. I might have said squared x cubed in there. Okay. So the derivative of negative or inverse cosine is negative 1 over the square root of 1 minus whatever's inside squared. So we're going to do that and perform that chain rule, whatever was inside here. So that's going to be my inside. I'm going to take the chain rule on that. So if I do that, negative 1 over the square root of 1 minus what's inside squared times the derivative of this, which is negative 15x squared. And then we can quickly reduce these negatives cancel. 15x squared goes on top. Negative 5x cubed squared is 25x to the sixth. We have our function. Nothing more than that. Pretty straightforward. Again, with these inverse trig functions, it's basically just knowing them, memorizing them, which is going to come from practicing them, plugging them in and following your chain rules. Nothing more than that. And most of the times we don't deal with it. I mean, this factor is down here, but we and rationalize, we don't mess with it. We just move forward with these. Okay, I'm not going to be too picky on you rationalizing. Every once in a while, we'll get one that we rationalize, and it does factor, and something does cancel, but it's unique cases. Okay. So the last part of 310 is derivative of inverse functions, and they do a great job in the book explaining it. So I'm going to save time typing up some examples and let you go into the book. So starting on page 219 of the book, they start talking about derivatives of inverse functions, and there's pretty straightforward of the formulas and how they work. So I want you to read through that. That way you can do the a couple of homework problems for this, and also with the worksheet. Remember, the worksheets aren't due, but they're just good for extra practice. Okay. So that's going to be the end of this video. Again, this is pretty much a pretty short lecture, but I wanted to keep it short so you could jump in and practice. I mean, normally we would be about the same speed in class. We just have a bunch of different examples we would practice in class. So jump into the homework, start working on that, practice on the worksheets, make sure you feel comfortable with these two sections and with 3.8. Don't forget about going back and doing 3.8, also implicit differentiation, which you really need to get done before you start these two. Remember, if you notice, I did some implicit differentiation in the examples we did in this lecture video. Okay, so go in and do those three sections. Also, I'll be posting with this email, or with this video, you'll see in the email when I send the email out about this video that I've posted the discussion, and make sure that not only do you submit the discussion online on Moodle, but also bring a copy of what you submitted to class, and I'll make note of that in the discussion itself, because we will need that in class on Tuesday. Okay. Other than that, if you have any questions, just send me an email, and if not, I guess I'll talk with you soon.